am Amanda Kocher, and this is Boyle's Law and how it relates and causes ventilation in the human respiratory system. All right, so let's start with Boyle's Law. Boyle's Law essentially states that there is an inverse relationship between gas pressure and the volume of the space that that gas occupies. So it can be written in a formula that you could do a calculation as P1 times V1 equals P2 times V2. But essentially what you need to know about it is that as the volume of a space increases that a gas can be present in, the pressure of that gas will decrease. If our volume decreases, or when our volume decreases, the pressure associated on that gas goes up, which makes sense because you have the same amount of gas particles that have to exist in that space. If the volume is much larger in terms of space, then that pressure is going to be lower because those particles of that gas are going to be able to spread out and not be pushed together quite so tightly as they would be in a smaller volume space. I tend to think of it as people who are in a room, if they start out in a hallway in a school, for example, they may be very tightly packed together as they're trying to move into a gymnasium. And once they're in the gymnasium, then you have a much larger volume of space for all of those people or particles to occupy, and they're much more comfortable and able to spread out and move around a little more freely. So what does this look like in terms of ventilation in our lungs? So in our lungs, we have our internal pressure here. Outside of our body, we have our external pressure. And this is 760 millimeters of mercury. It is relatively equal between the external world and our internal state of lungs before we go to inhale. So just kind of at rest. But the other piece that's very important to look at here is that we have this 756 millimeters of mercury. So a slightly lower pressure is found in this blue space here, which is our pleural cavity. And our pleural cavity is filled with intrapleural fluid. So it's this fluid-filled space that doesn't have air in it. And it is at a slightly lower pressure than either the external world or our internal environment within our lungs. And you'll notice that each lung has its own pleural cavity, but they are at equal pressures. So what happens when we go to inhale is that we have our diaphragm, which is our major inspiratory muscle. So it allows us to inhale. It actually is going to contract and move down. Along with, we have our intercostal muscles that are between our ribs, within our rib cage. We have our combination of these two sets of muscles that are going to contract, and ultimately as they contract, they are going to expand that thoracic cavity. So you notice here in this light pink we have this thoracic wall. So as this expands, so our diaphragm is going to be moving down, and then all of our thoracic wall here all the way around is going to be expanding. And as that expands, it increases the volume of space within our lungs that could be filled with a gas, okay, the air that we breathe in. And so the pressure is going to decrease within the lungs. And when the pressure decreases within the lungs, that is what is ultimately going to pull air into our lungs, in through our trachea and bronchioles, down to the alveoli, and actually let those alveoli expand. And in an ideal situation, this is able to happen regularly without any extra strain on our muscles. Then when we go to breathe out or exhale, what is going to happen is that diaphragm is going to relax. So when the diaphragm relaxes, it will return to its kind of upside down U here. So it pushes up on those lungs, allows them to recoil fully so that they can go back to their original resting size, their not stretched size. And what's going to happen at that point is the pressure within the lungs, because again, we had all of those particles come in and we had, nice space like in our gymnasium, but now the event's over and now we have to force all those people, all those particles out of our nice big gymnasium. But in this case, our gymnasium is actually getting smaller and our lung is going to decrease in size. So volume is going to decrease, which puts extra pressure on those particles. And so they are going to try and follow the path of least resistance and will be exhaled from the body. So to shift a little bit into, so what does this look like maybe when this isn't in our ideal situation? So chronic obstructive pulmonary disease is one of the most common diseases in terms of pulmonary disease and is an incredibly deadly disease. It's kind of a group of diseases that includes emphysema, and is very common in smokers. So in COPD, we see an increase in airway resistance, and so it requires a greater pressure gradient to maintain normal airflow, inhaling and exhaling for that person, which is going to increase that muscle exertion requirement that we have on those intercostal muscles as well as the diaphragm to allow air to come in and out. And so that is very important as we look at kind of pathology in terms of our respiratory system as well. So one study that has been done, it actually was a review of several studies over a great period of time, was looking at this concept of lung hyperinflation, which is a common thing in COPD, and it's just defined as basically an abnormally high volume of gas that remains in the lungs even at the end of expiration. So the goals of this study were to kind of get a greater understanding of COPD and how it works, like what does it actually look like from a physiological standpoint, what does it have to do with when we talk about pressures of inspiring and expiring or inhaling and exhaling. And then it kind of shifted into kind of how do we measure lung hyperinflation in COPD patients, and relates that in clinical findings to emphysema and how hyperinflation looks in emphysema patients. It discusses potential mechanisms for causing hyperinflation of a lung, as well as if that lung hyperinflation is reversible or if it is permanent. So it starts off by kind of introducing the idea of what does lung hyperinflation look like in COPD and why is it really important to look at. So what we see is within our healthy normal lung, so that's kind of what this is showing you, we have our values for the inspiratory reserve volume, we have the tidal volume, expiratory reserve volume, and then that residual volume. So the three areas I want to bring your attention to are the expiratory reserve volume. So here we have the expiratory reserve volume in the normal lung, and the obstructive lung is decreased. The residual volume is increased greatly between our obstructive lung and our regular lung, our normal lung. And then also that total lung capacity. So the total lung capacity is all the way from the bottom to the top of the gray boxes. That's what's considered the total lung capacity. In the obstructive lung, that lung capacity actually increases as well, which is what indicates the state of hyperinflation. The severity of COPD in a patient is highly correlated with lung hyperinflation, which brings us back to kind of the purpose of this study and why it was developed. So the Global Initiative for Chronic Obstructive Lung Disease, or GOLD, has gone through and made a scale for COPD based on measurements of airflow limitation during forced expiration. So the FEV that we see in this table looks at the forced expiratory volume in 1 second, and based on how that measurement reads, if it is less than 70%, when the predicted is over 80%, then we just see a mild COPD case. As that FEV continues to be lower and lower, so the volume that is able to be exhaled under forced expiration, as that decreases, then we work our way down this table into the moderate, severe, and then ultimately very severe COPD. So there are several different ways that you can measure for lung function, and there's advantages and disadvantages to both. So in this particular review, they just quickly went through some of the advantages and disadvantages of 6 of the more common methods. Granted, some of them, so spirometry is very simple, it's common, it's easy to get multiple measures, but it cannot measure that residual volume, which is one of the challenges with it. However, that's one very specific disadvantage, whereas we have several in here that their disadvantage is just kind of the lack of accuracy. And then the forced oscillation technique, which is actually in several studies that are looking at the effectiveness of this technique. At the time of this review, it was still in very much that early stages of needing more evaluation, more testing to see if it is great. But one of the big advantages of it is it's very sensitive, but it also doesn't require a lot of patient cooperation, whereas some of the other methods require a little bit more on the patient end. So ultimately what this gets us to is that lung hyperinflation is complex, but it's definitely something that we have found correlates with COPD and the severity of COPD and how it's developing in a patient. And so looking at this, we have, you can have your airway narrowing. It's beginning to narrow. What does that cause? If it causes that reduced lung elastic recoil, so that the lung's ability to return back to its resting state completely for those alveoli to close, then that is a big deal, obviously. And if we increase our residual volume, increase our total lung capacity, or increase our functional residual capacity, any of those things will lead to a hyperinflation, which ultimately correlates with that end of severity of disease. Because that hyperinflation so closely correlates with the severity of the disease, looking for improvement in hyperinflation in COPD patients is one of the important criteria for evaluating the effects of therapeutic drugs moving forward. Thank you so much for listening.